Okay, so welcome everyone in the post-lunch session of today. So the first talk is going to be about non-BPS microstates in ADS3 by Anthony. So over to you.
All right, thank you. First, thanks to the organizer, Nick and Jose, for organizing this conference and giving me the opportunity to talk. So today I'm going to present a work that's been going on for a few years with these people, Bogdan, Stefano, Rodolfo, and Nick. Half of them are here in the audience. So the topic is about non-BPS microstate geometries in 3 dimensions in asymptotically ADS space. And the idea is that we're able to build non-supersymmetric microstate geometries that are inspired from superstrata. So if you don't know about superstrata, we already heard a little bit about it in the conference, but I'll present them in a few minutes. As a forward, the idea is that we can sort of create non-supersymmetric generalization of superstrata that are based on the same constituent as superstrata, but arranged in a way that the result is non-BPS. And so we can, for example, take some left-moving superstrata that preserve a certain set of supersymmetries, and right-moving anti-superstrata that preserves another set of supersymmetries, and then when we clash them together, and we get a geometry, and the result is non-supersymmetric. So this is what I'm going to talk about. First, I will tell you a brief introduction on microstate geometries, and in particular non-BPS microstate geometries, and why they are relevant for in the context of the fuzzball proposal. Then I will explain you how we actually can construct those non-BPS geometries. So here, as soon as we talk about something non-BPS, the complexity jumps a lot because we don't have access to the BPS equations, and we have to solve the equations of motion. And so I will show you how we can actually build those non-BPS microstates in a very specific theory of 3-dimensional supergravity. Then when we've done that, I will then tell you how we can interpret those geometries in the CFT, and how we can actually get a glimpse on the holographic dictionary between those states and the CFT states, and how we can use it. And finally, I will tell you about the very interesting properties of the solutions that we've called the spatial locus. All right, so let's start with the very basic. We all know that black holes, they have thermodynamics properties. They behave like black bodies. They radiate. They have a certain temperature. They are gain temperature. They also have an entropy that is proportional to the area. And when we have an entropy like this, we want to actually be able to interpret it in terms of counting of microstates. So this is the Boltzmann formula. We want that the entropy is proportional to the logarithm of the number of microstates. And this is already in contrast with what we can do in general relativity, because in GR we know that there are some uniqueness theorems. And so in 4-dimensional GR, there is only one black hole state. And so we are not able to reproduce this entropy. So we have to go beyond GR. And one way to do it is actually to use string theory. And one of the great success of string theory is that it is actually able to access all the microstates of the black hole. So it is possible using string theory to actually account for all the microstates, with a few caveats that this counting works at weak coupling when we are very far from the regime where a black hole exists, and it's also for supersymmetric black holes. So what we want to actually do is to understand what those microstates become at strong coupling, and also what is the role of the horizon for those microstates. So here I will then work in the context of the fuzzball proposal. So I'm going to try to motivate why the fuzzball proposal can be a valid conjecture. And we can make a few observations. The first is that if we consider pure states in string theory, then pure states, they don't have an entropy. But by definition, the entropy is 0. And if you want to believe the formula that the entropy is proportional to the area of the horizon, you don't have to believe this formula in general because it's a semi-classical result. Maybe it's not in the full quantum gravity, but if you want to believe this formula, then it means that the pure states do not have a horizon. Then we also know that there's another problem with black holes, that is the information paradox, that we cannot recover the information that is thrown inside the black hole. And we know that one way to solve this paradox is to involve horizon scale, to involve corrections of the geometry at the scale of the horizon. And this is something that's very hard to do using standard particle theory, because if you try to build some structure at the scale of the horizon, it tends to fall inside a black hole. But in string theory, there are actually some some ways to construct this kind of microstructure. And for example, we can consider bound set of branes. And this kind of bound sets, when you increase the gravitational coupling, instead of collapsing, they tend to grow in size, and they grow at the same rate as the Schwarzschild radius. So we can believe that using this kind of ingredients, we can build microstates of black holes. So this leads to the Foswell proposal. The idea is that there must exist exponential s e to the s microstates that are horizonless, but that have structure that at the scale of the would-be horizon. And then black holes are not real states of the theory. They are not real solutions of quantum gravity, but instead they emerge as an average. So if you don't have enough degrees of freedom to distinguish between all the microstates, you have to perform some kind of averaging. And what you get is actually black hole geometry. All right, so those microstates, all those microstates, they will typically be very stringy, very quantum, and we're in a regime where the coupling is large, and we're in the strongly coupled regime. So building those microstates is something that can be very hard. But what we can do is actually there's some very coherent excitations of those microstates. And if these excitations are coherent enough, then we expect that we can describe them semi-classically, and so using supergravity. And this is a picture to have in mind. So to the left, we have the classic black hole geometry. So asymptotically, we have flat space, and then we arrive to a throat. Then at some point, we hit the event horizon, and then in the end, everything finishes at the singularity. And we want to replace this geometry by this kind of microsets. We call them microset geometries, where they are the same asymptotics of the black hole, but instead of having a horizon at the scale of the horizon, we have something that caps off smoothly, and we have a very well-defined and smooth geometry. All right, so this has been going on for many years, and we know now of a lot of these kind of geometries, but most of them that have been built today, they are supersymmetric. And the reason is simply because we know how to solve the BPS equations in some cases, but it's much harder to solve the equations of motion. But we know that if we want to solve the information paradox, we must have an understanding of what happens to the Hawking radiation. And the Hawking radiation only exists for non-extremal black hole. You need some temperature. And so we want to actually be able to understand the microstates of non-supersymmetric black holes. And it turns out that in the literature, you can find a few non-BPS solutions. I've listed a few of them here. One of the first and the most famous is JMART. And then we also have some very interesting new solutions that Pierre is going to talk about in a few days, and maybe Ibu as well. But among the solutions, there's only one family that has an established dictionary. This is the JMART solutions. And JMART, they are very atypical solutions because they have a very large angular momentum. And if you try to look at if you try to look at them in a phase diagram, you see that they lie outside the BTZ threshold. They do not correspond to real microsets of BTZ. So in this talk, I'm going to show you how we can actually build microstrata that are those new non-BPS microsets that are actually in the more typical region of the phase space. And as I said, there will be more like some kind of non-BPS generalization of a superstrata. And so we'll be able to actually establish also a holographic dictionary. All right, so how do we do that? First, let's see what the setup is. So we start with the D1, D5 system. Emil already introduced it a bit. The idea is that we start with the type 2B string theory. We have 10 dimensions. And then we compactify 5 of them. We will single out one of them. So we will write these 5 dimensions as a 4 torus and then a circle. This circle is generally called Y. And we will take the size of this circle to be much larger than the size of the torus. And then on this system, we will put a bound state of D1 and D5 branes, so that the D5 branes actually wrap all the 5 dimensions, the 5 compact dimensions, and the D1 branes wrap the special Y circle. This system is still supersymmetric. And if we back-react them, what we see is that in the decoupling limit, in the near brane limits, we find that the geometry is that of global ADS3 times S3. So this is a ground state. And if we want to excite this system, we can add a third charge. We can add a momentum charge along the direction y. And typically what happens to the geometry is that the sphere will get some deformations. The whole D1D5 system, we know that it is dual to a two-dimensional CFT because it is asymptotically ADS3. And this CFT is called the D1D5 CFT. It has central charge 6 and 1 and 5. And it's actually, it has a target space that is a simple symmetric product of a NT4, N-sigma model on NT4. All right, so what about superstrata? So superstrata are built exactly this way by adding a left-moving charge, some excitations. And so that break half the supersymmetry of the ground state. And superstrata present themselves like this. So asymptotically, we have an ADS3 region. That's what we expect. Then when we hit some scale, we hit the scale of some parameter B. We see that the side of the circle stabilizes. And then we get an ADS2 throat. The DS1 stabilizes. At some point, we hit another scale that is given by this parameter A. And then the caps off smoothly. This is the scale where we have some modes, some superstrata mode. And you see that if we didn't have this scale, if we take A to 0, then we would get an extremal BTZ throat. So by taking A to be very small, we are in the deep scaling regime. And we have geometries that approximate very well the BTZ black hole. So we know that we know the holographic dictionary of superstrata. They are dual to states of this form in the CFT. So we have a certain number of strands that are vacuum that are given by this parameter A. And this parameter A also corresponds to the angular momentum of the geometry. And we also have a certain number of strands of this type here, which are descendants of a primary of length k. And the number of these strands is also controlled by the parameter B, which controls the momentum charge of the geometry. All right, so now we know what superstrata is. We want to construct non-BPS geometries that are built on the superstrata. So let's see what we can do. We will first focus on a single mode superstrata. So let's look at just at a simple strand of superstrata. We take the simplest superstrata, the 1, 0, n. So the strand looks like this. We want to build something that is non-BPS. So there are essentially two ways of doing this. We already have left-moving excitations, so we want to add right-moving excitations. One of the simplest way to do it is maybe the most naive way. So we know we have some left-moving excitations, so we can say, let's add some right-moving excitations as well. So we add a certain number of, we act a certain number of times with this operator L till -1. This strand here breaks all the supersymmetries. Another way to do it is actually it's maybe a more subtle way. It's to keep the same kind of strand as the superstrata, strands like this. But we can also add other kind of strands with strands where the right moving spin is actually, we flip the right moving spin. Instead of having a spin of a half, we have a spin of -1/2. And what you can see is that individually, each of these strands preserves some supersymmetry. But when we put them together inside a heavy state in the full CFT, then we break all the supersymmetries as well. And those kind of states, those are the microstrata that we will then be able to construct in supergravity. All right, so as I said, to construct them in supergravity, we'll need to work in a very specific theory in 3 dimensions. And so this comes from this paper here. They made the observation that all the interesting physics that happens for superstrata, asymptotically ADS superstrata, can actually be encoded inside the three-dimensional spacetime. So here's the idea, very schematically. We start with a type 2B supergravity in 10 dimensions. The first step is always to reduce on the T4 to get a theory of supergravity in 6 dimensions. This is a theory in which superstrata and most microstate geometries have been built. And then what we can notice is that when we look at a particular family of superstrata, the one that have strands of length 1, then there's only a very, very restricted set of modes that are activated on the sphere. So the matrix schematically it looks like this. So you see that there's no dependence at all of the angle of the sphere, and there's also a very simple dependence in the parameter theta. And it turns out that with this kind of metric, we can write consistent truncation and describe the geometries entirely in a in a 3-dimensional theory of supergravity. So this theory is gauged because we compactify on a manifold that has some curvature. The gauge group is simply the isometries of the sphere.
metric does not depend on psi, but it depends on theta.
It also depends on psi. Yeah, here R is also R and psi. I wanted to point out the dependence in theta. I didn't want to. Yeah, but there is a dependence in psi as well. All right. So the important part about the constant truncation is that if we build a state in the three-dimensional theory, then we can uplift it directly to a state in the six-dimensional theory. So it's not like an approximation where we kind of solve the equation of motion up to a certain energy scale or things like effective field theory. Here, with the constant truncation, solutions are directly mapped to the solutions of the higher dimensional theory. So this is what the theory looks like. It's maybe a bit intimidating, but it's actually we can recognize some of the factors. So this is the bosonic axiom. We have some gravitational term, then we have kinetic terms for all the fields. It's a theory in three dimensions. We also have a Chern-Simons term, and then we have some coupling because the scalars are charged, and then a potential for all the scalars. So this theory has as I was saying, the vacuum is simply global ADS3. And so we can write it in this way. You recognize the ADS3 metric. Here, this variable sigma is actually what I was calling the circle Y, but we write it in a way that is scale-free. And all the other scalars take this form. So the scalar chi, sorry, is that? Yeah, I missed this slide here, sorry. So here, this was a visualization of the field constants. We have a metric, three-dimensional metric. Then we also have this matrix of scalars, MAB. And this matrix of scalars actually encode for the deformations of the sphere. So those are the shape modes of the sphere. And then we also have a matrix of gauge fields, A, that encode for the vibration of the sphere on the ADS3. Then finally, we also have a vector of scalars, chi A, that are actually the main momentum carrier, and they are encoding for the B field. So yeah, so knowing that, we can look at what the scalars are. And so chi A is simply 0. That means that in the vacuum, there's no B field. Then this matrix M is the identity. This means that the sphere is actually round. And this matrix A is also 0. And this is because the vibration between the sphere and the ADS space is trivial. It would also be convenient to introduce a new coordinates for the for the radius because of the way we do the numerics and the perturbation theory. We want to have a radius that is compact, and so we will define this coordinate psi that will actually be bounded between 0 and 1, where 0 is the original space and 1 is at infinity. And if we use these coordinates here, along with also this left-moving coordinate, we can write the metric in this way. So now we have the vacuum. We want to look at normalizable perturbations on top of this vacuum. The method for doing that is to first look at the equations of motion and linearize them. And then we try to build separable solutions. We want the solutions to be regular because we want to construct smooth geometries, and they must fall off at infinity with the correct rate. So what we find is that first we have what we call the alpha-1 class of perturbations. Those are perturbations that are dual to this kind of state in the CFT. So notice that it depends on two parameters, n and m, two mod numbers. And when m equals 0, we actually find that the solution is supersymmetric, and it is actually the superstrata. So we already know how to build some of those states. We know how to build the superstrata. Then we also have a second class of normalizable perturbation. We have what we call the beta class. And this starts from a different chiral primary. It still has two parameters, n and m. But you see that this time the chiral primary has a spin 1,1. And when m equals 0, this is also a supersymmetric state. So this is a kind of superstrata that has never been built in 6 dimensions. And this is something that could be explored. But in this talk, I will mostly focus on the non-supersymmetric side of the story. So yeah, we have these two classes, alpha-1 and beta-1, and it turns out that if we look at another sector of the theory, we also have alpha-2 and beta-2. That is simply what I was saying at first, that we can flip the sign of the right spin. So we want to compute the back reaction of those normalizable perturbations. And the trick to do that is to use a very particular ansatz that we've named it the Cuban ansatz, because the idea is the same as the construction of cuboids. The principle is that we make an ansatz where the scalars can have some time and some angular dependence, but we tune it so that actually the currents and the energy momentum tensor do not have any time dependence or angular dependence, and so that in the end the equations of motion will depend only on only one parameter, the radius, and so all the complicated partial differential equations that were the equations of motion become much simpler. They become simply ordinary differential equations. So the ansatz looks like this. We have we have 4 fields for the scalars, and we have a very particular. You see the very particular ratio between the angular dependence and the time dependence that we put in the scalar here and the scalar there. There's a 2-to-1 ratio, and this is what is very important to have equations of motion that do not depend on these variables. And then we also have other.
Bonjour à toutes et à tous, Christian Bailly, directeur du centre CEA Paris-Saclay. Ce message est destiné à l'ensemble des salariés de l'établissement Paris-Saclay, électeurs aux élections professionnelles. Le 7 juin, à partir de 10 heures, je répète, le 7 juin, à partir de 10 heures, vous serez appelés à voter pour élire vos représentants du personnel au comité national, au comité central des activités sociales, au comité social et économique du centre CEA Paris-Saclay et au comité local des activités sociales du site de Saclay et du site de Fontenay-aux-Roses, Évry. Ce vote s'effectuera de façon électronique sur votre lieu de travail ou à distance pour l'ensemble des électeurs. Ainsi, vous aurez la possibilité de voter durant l'intégralité du scrutin à partir de tout appareil connecté à Internet. Votre vote sera déterminant pour les 4 années à venir. Aussi, je vous encourage vivement à participer à ces scrutins. Vous aurez jusqu'au mardi 13 juin, 12 heures, pour voter. Je répète, vous aurez jusqu'au mardi 13 juin, 12 heures, pour voter. Je vous remercie de votre attention et vous souhaite une excellente après-midi.
All right, so let's get back to this. So we have this ansatz. It has 11 functions of only one variable, the radius. And this ansatz actually contains 2 types of those normalizable perturbations that I was discussing about just before. There's the alpha perturbation that is encoded by the scalar nu1, and the beta perturbation that is encoded by the scalar lambda1. Actually, as I was saying, there's also other kinds of perturbations, this alpha2 and beta2, and we can also include them in an ansatz that is a bit more general, and we need this time 19 functions to define it. So we want to compute the back reaction. We have a very simple model. We have only dependence in one parameter, but we have 19 functions and 19 equations. And so those equations are nonlinear, and so there's no real hope to. Sorry. Okay. Okay. So we want to compute the back reaction, and we cannot do it analytically. So we have 2 different methods that we can use. We can either use perturbation theory, or we can actually solve the equations numerically. Using the first method, we're actually able to solve the equations of motion perturbatively around the vacuum to very high order. So we can check that the solution is completely smooth and well-defined up to 4th order in general for general mode N and M. But we can also do it for specific modes. We can check that the solution is very consistent and completely smooth up to 10th order or even more. There's really no limit to what we can compute. There's just the computational time that it takes to check it, and it works to very high order. Then numerically, we can also solve the equations. And here we can use either a double shooting method where this is where it's important to have a compact radius, because we can shoot from one end of the segment and then shoot from the other end of the segment, where we specify the boundary conditions, and then we meet the solutions in the middle, and then it becomes an optimization problem to construct the solutions. The other method is also using a Newton algorithm to solve the equations. So we linearize the equations around the solutions that we're supposed to be known, that we're supposed to know, that we're supposed to be known. And then we start with a seed solution that is close to that we're supposed to be close to the actual solution. And then we make a certain number of iterations of the Newton algorithm to get closer and closer to the solution. And using these methods, we can actually solve the equations of motion with a very high precision, up to 10 to the minus 50. So that's even higher than the standard precision of the standard machine precision. And this is the kind of result that we get. So here it's still close to the perturbative regime. So what we see, this is the 11. Those are the 11 functions of the ansatz. And what you see is that first, the perturbation theory and the numerics match very well. And all the functions are smooth. The asymptotics are the correct ones. And so we can build this kind of solutions. Here on this graph, it is the alpha 1 class of solution. And so when we backtrack the system and obtain this kind of solutions, what we see is that the dual will have this kind of the safety dual will have this kind of form. This is still in the perturbative regime, but using numerics, we can actually go in the non-perturbative regime, and we can go in the regime where the throat is very long, and we have a scaling geometry. So here, what we represent is the size of the Y circle as a function of the radius. Here, the radius is on a log scale, and so what you see is that very far away, the radius increases with the radius of the Y circle increases with the distance to the source, and we have an asymptotically ADS3 region. Also, when we are very close to the center, the radius goes to 0, and we have a cap. This is what we expect from the geometry. And then you see that here, as we go closer and closer to the scaling limit, we have a plateau. This plateau corresponds to a stabilization of the size of the Y circle. And the longer this plateau, the higher the redshift. And you see that we can get, this is a log scale, so this corresponds already to four scales, and we can go to very high redshifts. Here it's a different class of solutions than the previous one. Before it was the alpha class. Here it's the beta one, the beta 1 class. So, but the result is really the same. And to show you that the numerics are very reliable, here's a plot of what is the error of the numerics. So on the x-axis, what we have is the number of iterations of the algorithm. And on the y-axis, we have the error. And so you see that as we increase the number of iterations of the algorithm, the error goes down exponentially fast. And when we are to 200, sorry, there's a question, Nick.
I think this is an error on my side. The x-axis is the number of grid points used for the numerical simulation.
Sorry. So this is the number of grid points, and when you have a sufficient number of grid points, then we can have a very, very high precision on the numerics. All right, so I hope that I've convinced you that the solutions that they exist and we can build them. So now let's see what we can do with them if we can identify the holographic dual and what we can use how we can use the ADS-CFT dictionary to learn more about the solutions. So here we'll focus on the alpha 1 class of solutions. And if we look at the back-reacted CFT states, it will have this form. So this is the strand that we started from. And when we backtrack the solution, we added progressively more strands of this form until we have a heavy state. And we want to match it with the solution in the bulk. And making a precise matching is a very hard problem because we can do some very precise holographic matching when we have supersymmetric states, because in the CFT we can compute things at the orbifold point, at the free theory point, And in the supergravity is very far away from this point. But in general, when we have supersymmetry, most of the computations that you do at the orbifold points, they can actually be matched directly with the computations at the supergravity point because they are protected by the supersymmetry. Here we do not have supersymmetry, and so nothing is protected. And it means that it's very hard to do any kind of matching. But there's something still that we can do. We can match actually quantities that are integer valued, because as we move in the modular space, those quantities will not be able to change. So those quantities that are simply the angular momenta, the true angular momenta, and the momentum charge. And so if we use these quantities and we use the standard Pfefferman-Graham expansion of the metric to compute them holographically, what we can do is that we can actually determine what is the exact frequency of our solutions, the frequency of the scalars, and we can also determine what is the energy of our solutions. And we can compute then these energies at strong coupling. And in the CFT, they correspond to anomalous dimensions computed at strong coupling. All right, so this is the result. And what we find is, this is a perturbative computation here. We find that there's a shift in the frequency of the solutions as we go to higher orders in the perturbation. So naively, the frequency is an odd integer. This is what we find from the normalizable perturbation. But when we add corrections, we add a negative correction to this frequency. It takes this form, and you see it depends non-trivially on all the parameters of the perturbation. And this frequency shift, what we can see is that we can interpret it as the binding energy between the pairs of the non-BPS strands. And the fact that it is negative means that the binding energy is actually really a binding energy. It's a negative energy. And we see that it depends on all the modes number, the modes number n and m. It also depends on what class of solutions we look at, and what is the amplitude of the perturbation. Yeah. So, as I said, this shift in the frequency, we can interpret it as a shift in the energy of the solution, and we can see directly when you compute the dimension of the state. So we can compute holographically h plus h bar, and we see that naively we have the value that we see for the perturbation at first order, and then it receives corrections at higher orders. We can also do the same computation numerically. And so this is for another class of solution, but it works also the same way. And so when we are very close to the, in the perturbative regime, when we are very, very close to the vacuum, we see that we get straight lines, and we can actually check that this slope is the same as the one we get from the perturbation theory. And then it gets corrections, and it reaches finally -1 when we get to the CTC bound. And this I want to argue is a strong argument that we can actually maybe we can reach some kind of more chaotic regime when constructing non-BPS microstate geometries, because this is one of the recurrent criticisms of the microstate geometry program. That's we have supersymmetric states, and supersymmetry is very special because the spectrum looks like this. There's a very high degeneracy of states, and the gap between the states is very large for the one of the central charge. Whereas for standard black hole, what we expect is that the degeneracy must be completely lifted, and the gap between two states must be of order exponential -s. What we see here is that when we start with a perturbation that is when we start with a perturbation, we get something that is an integer, and so we see this gap of order 1 over the central charge. But as we increase the perturbation, we find corrections, and those corrections depend on the kind of perturbations, on all the mode numbers, etc. And this means that all of the states that were previously in the perfect line, they're actually completely lifted in different positions on the spectrum. So what we can see with this kind of states is that we lift completely the degeneracy. We cannot see for now, because we do not have enough states, that the energy gap will be very close, like e to the -s. But it seems to be an indication that instead of having this kind of spectrum, we're actually able to construct this kind of spectrum, the more chaotic spectrum, using microstate geometries. So now I want to turn to the spatial locus. So let me tell you what it is about. What we saw is that we have two kinds of perturbations. We have the alpha and beta perturbations. And if we look at it from the point of view of the CFT, there's absolutely no reason to believe that we cannot build them together in a single solutions. We have different kind of strands, and we can put them together in a heavy states, and this state is a perfectly valid CFT states. And there's no reason to believe that this state has any kind of problem. But what we find in the supergravity and in our three-dimensional theory is that for non-BPS states, actually, we cannot build solutions of this kind. The only solution that we can build, the only solution that is regular, is if we impose a very particular relation between the amplitudes of these two perturbations. You see that the amplitude of the beta perturbation must be quadratic in the alpha perturbation. And if we don't impose this kind of relation, then we find that at some point in the perturbation theory, we get some log divergences. This is not true for BPS solutions, and it will be important later. But so at first, it was a very perplexing result, but we can find the origin of the spatial locus in the way that we define our cube on ansatz. And the ansatz actually, when I defined it, I showed you that to make sure that the fields do not have any, the equations do not have any dependence in time and in the angular coordinates, we needed a very specific 2-to-1 ratio between the frequencies in each scalar. It turns out that if you want to construct a solution that involves both the alpha 1 and beta 1 perturbations, then the solution wants to break this ratio, because all the nonlinearities of the solution will generate other kind of dependencies. And if we want to describe this kind of solution within the cubal ansatz, then we find divergences. So the idea is that if we were able to construct a more general ansatz that includes more modes, more general solutions, maybe even complete dependence in all the parameters, then we should be able to describe this kind of solutions. So now maybe you're wondering, why am I actually talking about that? It seems like it's a bad point, like we were only able to do a very restricted set of solutions. Why do I want to point out this problem? Well, it turns out that this kind of solutions are actually very interesting. From the supergravity side already, what we find is that for these solutions, we have an enhancement of the global symmetry of the solution. So the vacuum solution has an SO4 symmetry. The vacuum is invariant under SO4. And generally, when we construct solutions, this SO4 will be broken to either a U1 symmetry or to no symmetry at all. This is what we find for supersymmetric solutions. But here, the spatial locus, what we find is that the symmetry is actually enhanced to an SO3 symmetry. This means that the scalar matrix M, the one that controls the shape modes, has actually 3 trivial eigenvalues. And the only non-trivial eigenvector of this matrix is actually the scalar K itself, the B field. So there's a non-trivial relation between the B field and between the matrix of shape modes. We also find this relation here that K is a null eigenvector of the field strength. So those are already properties that are intriguing in the supergravity. And note that for supersymmetric solutions, we can also place ourselves at the spatial locus, the spatial relation between beta and alpha. And if we do that for supersymmetric states, we also find the same properties. Whereas if we don't place ourselves at the spatial locus, we only have the U1 symmetry, as I was saying. So we want to try to interpret this result in a CFT. And this is something that we can use we can use the precision holographic dictionary to do that when we do it for supersymmetric states. Sorry. So as I was saying, doing the matching is very hard for non-BPS states, but for the supersymmetric states that we can build like this, it is actually possible to make a lot of computations and to match them. And so to introduce them, I will first have to to make a brief introduction of what is actually the undefined CFT. So the CFT has this target space here, symmetric product of n sigma model of NT4 sigma model. And the standard idea CFT dictionary tells you that when in the supergravity you have a field, it is dual in the CFT to light states, a state of whose dimension is of order 1. Whereas the back-reacted geometries, they are dual to heavy states that are whose dimensions are of order the central charge. This is something that we have already seen for example, the scalar nu, that we already identified its dual, which is a chiral primary of a dimension of a spin half-half. And here we are a bit more careful because we introduce also this copy index R that runs between 1 and n. And the important fact is that all the states that we build in the undefined CFT must be invariant under exchange of copies of the different copies of the target space. So this is what we get for the scalars nu. Now we want to build the heavy states that are dual to our geometries, and the heavy states will be multi-particle operators with a large number of these single particle constituents that we had before. And the choice of multi-particle operators depend on what perturbation we're actually exciting. What we see is that the standard single superstratum, the one with beta equals 0, when you have the alpha perturbation, and the special locus, the one where beta is at minus alpha squared over 4, those two geometries, they share the same initial perturbation. And so they are both back-reacted geometries from the same field. And this means that even though they must have different duals, because they are different states and the dictionary is 1-to-1, they must be made of the same light constituents. For the superstrata, the exact dictionary has already been built out some time ago. The exact state takes this form. It's a coherent superposition of states because it is describable within supergravity. But this term is very, very peaked at a certain value when this state has when we have n1 strength. And so we can approximate the state by writing it like this: n1 copies of the same strand. But notice that here I've put a star, and this is because this product is actually not the usual product as we understand it. As I was saying, any state that you build in the CFT must be invariant under the exchange of the copies of each T4 sigma model. And so there are actually several ways to construct states that are invariant. And it turns out that the way that we have to define the states for superstratum is actually this one. You see, we have to sum over all the states, but where each copy here belongs to a different, each strand here belongs to a different copy of the CFT. And in contrast, the usual way you want to define a product of operators is through the OP, this kind of OP formula. And this kind of formula actually does not give the same result as this one, because here, this operator S7, that is the dual of the field nu, it can act several times on the same copy of the CFT. So let's take a simple example to understand what it means. Consider the case where we have a very small number of states. We have only 2 copies of the CFT, and we have 2 states. If we look at this state here, which is the square of this simple sum with a star operator, we find these results. And essentially, if we want to look at each copy of the CFT as a box and each action of the operator as a circle, then it means that we can represent the states as a simple box, as this kind of diagram, with 2 boxes and a circle in each diagram. If you look at the standard way of constructing states, using a real product of states instead of this weird star product, you find that there are additional terms in the expansion, and there's also a state where we act twice on the same inside the same copy, inside the same box on the left, or twice on the right. So those 2 states are different. And the claim that I want to say here is that while the superstratum uses the starred version of the starred product the The superstratum state is the superstratum state is dual to a state that is defined using the stored version of the product. Then the state that is dual to the special locus is actually dual to the normal product of states. And this means that the special locus geometry is actually a gas of single particle states. And fundamentally, from the CFT point of view, it is simpler than the standard superstrata. Because this kind of construction, they can be generalized everywhere in the modular space. Whereas this kind of construction, they are very special to the orbifold point, where we can actually where we can identify copies of states, copies of the CFT. And first, the first thing that I want to say about that is that it's a bit surprising. First, that we have managed to build the standard superstrata before the special locus superstrata, because they appear much simpler. Both from the CFT side, we see that the definition is more natural, and also from the supergravity side, we see that they have an enhanced symmetry in 3 dimensions. So it's a bit surprising that we were able to actually construct those states before the special locus states. But also, it's possibly an avenue to make more progress and construct more supersymmetric states, because superstrata have been studied for a long time now, since they have been constructed, and we know a lot about their properties. But since they are very, they seem to be much more complex than what the special locus geometry is. Maybe what we could do is actually build. What we could do is build special locus superstrata, the most general one in 6 dimensions instead of the 2 dimensions that we've done here. And maybe there is a way to formulate the construction in a very simple way, maybe even simpler than the way the superstrata have been built with 4-dimensional flat plates. And this could actually, we could maybe learn a lot about the geometries of supersymmetric black holes if we could build this much simpler states. So I've made this claim that we have those 2 equalities, but I have not backed it up so far. So here's what we can do to actually prove that. It's not a complete proof, but it's some argument that says that this is the correct identification. What we can do is that we can compute 3-point correlators inside the CFT, and we can also compute them holographically and match them. And these 3-point correlators are protected by supersymmetry, and so we can really match them. For example, we can compute the VERs of dimension 1 operators inside the heavy geometries. Those are the 3-point correlators. What we find for the 2-charge solutions here only is that for the superstratum, this VER vanishes when the number of strands is the maximum number possible. And this is what we expect from the state with the stored version, because there is really only one state where everything is populated with only one action of the light state, the light operator. Whereas for the special locus, you see that the result is different, and the VEV does not vanish when n1 equals n. And this is because each state can actually, the operator can actually act on each copy of the CFT several times, 0, 1, or 2 times. And so when we compute the VEV, there's actually some freedom to go from one of the coherence, one of the ingredients appearing in the coherent states from one can go from one of the state to the other. The action of this operator is non-zero. And so this matches what we expect from the form of the CFT states. We can also compute the VEVs of dimension 2 operators. And what we see is that for the superstratum, there's one VEV that is non-zero, whereas for the special locus, all the VEVs of the dimension 2 operators are 0. And this is exactly what we expect from the CFT. This result comes from the fact. This comes exactly from the fact that we have this SO3 invariance in the supergravity side, and on the CFT side, it comes from the fact that it comes from the very definition of what is a dimension 2 operator. They are defined they are defined so as to be orthogonal to all the dimension 1 operators, to all the product of dimension 1 operators. And so we must find 0, and this is what we find. All right, so let me conclude. What we see is that we have been able to derive these non-BPS microstate geometries both perturbatively and numerically to very high precision. And so we can construct the supergravity dual to these kind of states. Using holography, we can actually compute the corrections of the total energy of these states at strong coupling. And it seems that it's the first glimpse towards finding a chaotic spectrum for non-BPS microstate geometries. And then we see also that we also seen that all the solutions share a special property that they lie on what we've called the special locus. On the supergravity side, we can see that they have an enhanced symmetry, and on the CFT side, they have a very clear interpretation as a gas of single particle states. And this leads us to several possible directions for the future. The first one is to be related with what I said about the chaotic spectrum. We want to be able to populate the spectrum more, to be able to see that the gap is reduced and eventually reaches exponential minuses. And to do that, we need some more general answers in the three-dimensional theory. And we need in particular to include multiple modes. This is not, as I was saying, this is not captured by the current answers that we've been using, but it still lies within the three-dimensional truncation. So it should be still possible to describe it in a somewhat easy manner. And for example, what we can do, what we should be able to do is to compute the back reaction of this kind of perturbation. All right, and another direction that we can go is trying to build solutions that are in the twisting sectors with strands of length k that are not one. And the reason we want to build this kind of solution is because the momentum perturbation is actually more localized inside the throat. And typically, the excitations fall off much faster at infinity when k is large. They fall off at like r to the minus k. And so this kind of geometries should be much closer to the black hole geometry up to a smaller point in the throat. This solution, though, they lies outside of the three-dimensional truncation. The three-dimensional truncation was very specific that the solutions have k equals 1. And so to build this kind of solutions, we will need to return to six dimensions. And we already know how to uplift the solutions that we have in 3D. We have some uplift formulas that take these forms. The idea would be to build an ansatz in 6 dimensions that would include all the solutions that we've already built, and then be able to generalize it so that it includes all the higher twist sectors. And then finally, there's the question of the Hawking radiation. To explicitly find and compute the Hawking radiation, we will need to couple our solutions to flat space. This is something that can only be done in 6 dimensions, and that is in principle very hard. It's not like for supersymmetric states where we can just add the ones in the harmonic functions. Here we have the solutions that we would build would be explicitly time dependent. But what we can do instead also is to try to compute the Hawking radiation directly from the ADS solution. And for example, we can do some computation, some kind of tunneling computation, or get some inspiration from what Emil was talking about this morning, and use the Hollar wind techniques. And yeah, I'll stop here. Thank you.
So questions?
Okay, so just to understand, clearly something I didn't completely catch. What? So you have, for the non-BPS solutions, a gas of supergravitons in the ADS.
Mm-hmm.
With some back reaction, or there is no back reaction yet?
Yes, there is a back reaction.
There is a back reaction, right?
Yeah.
So when you say gas, it means each particle can talk to each other particle. Each is back reacting on the other.
Yes.
It's fully back react.
Yes.
But the back react is still weak. I mean, you're close to ADS. Is that what you mean by linearized? You had the word linearized somewhere.
So here we can construct the dual to this kind of states.
Right.
So here the state defined like this with if n1 if of order the central charge, then it's a heavy state. And
so you can do that also. You can do n1 of order of the central charge. You can do
yes, but what we can do inside the supergravity, we do perturbations around the vacuum. So even though n1 is of order the central charge, it's still a small fraction of the central charge when we do perturbations. And also we can do numerics. And here for numerics, we can do the complete back reactions up to very large fraction of n1 over n.
But this one doesn't have the L1 tilde, right? That you need that to get the non-BPS nature?
This one actually is the when I write it like this, it's the supersymmetric one, and we have actually an analytic solution for the supersymmetric one. For the non-supersymmetric one, it would be superposition. We would have to take strands of this type and also strands of where the spin is flipped, the right spin is flipped with a minus a half here. And when we take both strands together, then the state is non-supersymmetric, and this is what we've built in the supergravity.
So what was the L1 tilde I was seeing in some of the earlier slides?
Yeah, this is one of the first actually. Let me go to the first ones.
Yeah, I think I can see it there. Yeah, that one.
Do you know how to put it in full screen? View.
Absolutely top. Look,
Top.
top.
Very top.
Sorry, here. Yes, okay, sorry.
Full screen.
Full screen mode. No, it doesn't. All right, so this is where we were. I was talking about two ways to break the supersymmetries of the states.
Yes.
One way is to do it like this. And so we have states like this. This corresponds to the alpha 1 perturbation that I was talking about with a non-zero mode number m. And we also have this kind of states. And this kind of states correspond to the superposition of both an alpha 1 perturbation and an alpha 2 perturbation. And both perturbations are supersymmetric on their own. But when we put them together, like here.
Okay.
So you see here that you have the alpha 1 perturbation that is non-supersymmetric and when m is non-zero. This is something non-supersymmetric on its own, but we can also have m equals 0 and also add strands of this type with also m equals 0. And when we put them together, then we get the non-supersymmetric state.
Okay, very nice. Thank you.
They can do that reaction to arbitrary redshift depths. So that's really strongly non-BPS.
More questions, comments? Well, if not, then let's thank the speaker again.
Stefano.
Yeah, next speaker is Stefano.
Uh-oh, that doesn't look good.
Whose laptop is this?
Whose laptop? I don't know.
It might be.
Is this Maxim's laptop, Joseph?
It might be Maxim's.
Shall we call?
And I'm about to discover all sorts of secret. Oh, this looks promising. Is this you?
No.
Okay, maybe we need to get Max. Can you call Max in?
Okay.
Oh, okay. Oops, there was an error. That's try again.
Why do you open with Adobe and not with?
It's just because of.
Open up with the other one.
I'll try that.
No.
Oh no, cannot be opened. Here's what's a different type of. What is a PDF?
Maybe she just come up.
Just call Max in. Okay, change now. Go back to open with and see if we can just open with now there. I was going to be reading.
I don't think.
Okay, maybe that will work.
No.
Skim. Just close it again. Try open with Acrobat again. Open with. No.
Open with. He's
Click
suggesting
OK.
Acrobat.
Open with. There we go. Just try that.
But that's the same thing.
Oh shit! There was an error. Maybe this files got corrupted.
I said tomorrow, this morning, it said it was okay, so I have no idea why there is a problem.
It's okay. Don't worry.
I can take my leg. No, I don't know.
No, leave.
You can always take a laptop. There's no problem. You can just, there's just one connection. So, you know.
You can send it. This was okay.
It doesn't go.
We don't know how to open it.
Open it. It says there is an error.
Sorry? What? I would write it's extremely well. Don't insist, but make it very clear that I don't know, sorry. I don't know why. Is the file corrupt? Perhaps you have another copy of it you can. Actually, let's try and all this. Let's just check through the back. Yeah, so Nate's file opens.
Mine just opened.
Yeah, but I think it's a good problem.
Well, something might have got corrupted, but
Yeah.
can happen.
So the same again?
No, he copied it. Should be
It may
fine.
be.
On the stick there.
Yeah, this will open. That looks promising.
Sorry. Still opens. Oh,
Yeah.
oh, it seems to work. Okay, good. Well, good. So, yeah, just got corrupted. Looks good. You use the bottom one? Thanks, Maxim.
Okay, so let's get started with the next talk by Stefano, who's going to tell us about exploring fuzzballs with worldsheet methods. So,
Thanks. Can you hear me? Thanks for Nick and Joseph for setting up the fifth edition of this nice workshop. Thanks for asking me to speak. So what I'm going to talk about is, well, I'll try to give a bit of an overview of what we have been doing over the past years together with Emil and David. And I'll try to, not to dwell too much into all the glory details, try to give a bit of an overview. And then if you're interested to know a bit more the technical details, we can discuss. Maybe I don't need to do too much of an introduction to this audience, but let me just say a few words. And Anthony said almost the same thing before, but let me just repeat. So of course we know that So black hole emit a thermal radiation, losing the information on the initial state. And computing quantum correction that restore unitarity, unitarize the Hawking radiation is, of course, a major challenge for any theory of quantum gravity. Sorry, I wanted to. Okay. But this is not just a technical challenge. Okay, if you think about this problem, there are deep paradoxes that arise because of this information loss problem, and essentially they stem from the tension between any information transfer mechanism that you can think about and the causal structure of the space-time as dictated by the black hole solution. And this seems to lead to some sort of apparent violation of effective field theory at the horizon scale, as was pointed out by Samir a few years ago in a nice no-go theorem that sort of seems to imply that in order to solve the information paradox and unitarize radiation, you need to have some sort of structure at the horizon that stores information of the black hole. And if you insist to having smoothness at the horizon scale, you're sort of forced to have some sort of no localities, okay? So what we want to do is to try to formulate these problems, okay, more concretely in string theory. And the reason is that in string theory, we have control over the microscopic degrees of freedom that store the black hole entropy, okay? And so we want to try to rephrase this problem as to understand the effective theory, essentially, the property and effective theory of these degrees of freedom. However, there is a problem. This picture, this microscopic picture that we have in string theory is valid only at a special point in the moduli space where we have adiabatically switched off the gravity interaction, and we are left with strings and branes in flat space, okay, as Andrea nicely reviewed in her talk yesterday. So we will focus on a particular configuration, as Anthony was and Emil were reviewing in the talk before. That is just the simplest of all situations that where we understand very well the microscopic degrees of freedom, which is the Strominger-Vafa black hole. So we have the D5, D1 P black hole, and the system has, Anthony already introduced this before. We have some stack of D5 branes wrapping a T4, a small T4 times a circle, which we will call SY. I should press this. And then we have some D1 branes wrapping the SY circle. And then there is some, we have some units of momentum along the SY. Okay. So so when we are at the point where these branes are just in flat space with the coupled the gravity interactions, we know how to reproduce the entropy of the black hole. And in fact, the entropy is stored essentially by an effective strings that stretch between the D1 and D5 branes, which is an effective degrees of freedom that wrap a circle which is n1 and 5 times bigger than the SY radius. That leads to a momentum fractionation in unit of this effective radius, and that's essentially the main mechanism that permits to reproduce the entropy. The same system can be described by CFT, and at a certain point in the modular space is just the symmetric orbifold CFT that Anthony introduced before. So, okay, so what we want, so at this point we understand what is happening. What we want to ask is essentially how do this microstate look like in the gravity regime, and what is their effective theory, and what is their effective causal structure that those degrees of freedom, this microscopic degree of freedom fields. Naively, one could expect that as gravity becomes stronger, these brains shrinks and get engulfed by the horizon, and we are left with some microstate confined at the UV scale. But in fact, brain bound state can expand as the coupling is increased, and their back reaction is described by some smooth horizonless microstate geometries, which provide a concrete mechanism to hold the structure at the horizon. And sorry for, I have not been too careful about citation. Of course, many people in the audience contribute to this program, so I will not just put all the names. The problem is that, okay, these kind of microstate geometries that have been constructed so far represent some non-generic coherent state, and they do not reproduce the black hole entropy. Okay. However, there are still a very useful solution, okay, that I will call classical island, nothing to do with the islands that are fashionable nowadays. And so this coherent state, if we suppose to inject some energy to the system, we expect that they will decay when perturbed, and there will be an evolution in the phase space toward the most typical sector of the phase space. And this was also described by Andrea in some paper a few years ago. What we want to do is to explore this evolution in the phase space toward the most typical sector. And so in order to do this, we are interested in asking, okay, let's start from one of these nice classical coherent solution, and we want to explore the phase space, okay, around that particular solution. And we will show that, in fact, worksheet techniques are useful for this purpose, and they permit to explore the phase space, not being confined in the supergravity approximation, but we can explore structure and and excitation that lies beyond the supergravity limit. So what we can expect in exploring this microstate phase space is something like this, okay? So there is a simplest of all possible ensemble of solutions are solutions which are well described within supergravity, and they just correspond to microstate of the two charge black holes. So we just switch off one of the charge. This is very well understood. And then we can do more and explore a subset of the phase space, which is populated by this microstate solution, which have a nice description in supergravity, and they correspond, and they have three charge. Okay, but then we can we expect that there are there can be more kind of solution where we cannot just use supergravity. For example, we can think that there are some solution where the supergravity solution is allowed to have some kind of singularity, which, however, is resolved in the full string theory. Okay, and that's what we will call three-charge stringy microstate. And these are sort of the ensemble of solution where if you have control over in string theory, you can describe, but this is the green color means that those are the set of solutions where string perturbation theory is a good expansion. But then you can think that there might be just some generic fastball where even just string perturbation theory in G string breaks down and it's a fully quantum solution. So we want to set up some tools to explore this phase space, and we will see that we sort of encounter example of all these kind of sets. No, I need to press it. So as I was saying, so the simplest of all possible cases is just to focus on two-charge solutions, and where essentially everything is understood. The two-charge microstate geometries were constructed by Lunin and Samir a few years ago, and we will actually work in the S-dual frame, the NS5F1 frame, because we aim at having some sort of worksheet description of some of the solution, and so we need to ensure that the solution do not source Ramon-Ramond fields. And so this class of solution is well known, and the metric and the B fields are encoded by some harmonic functions, which are fully specified in terms of some profile functions that essentially encode the profile of these 5 branes in transverse space. And in some cases, these integrals can be performed explicitly, and one can just work out the solution in a very explicit way. So although I will try not to talk too much about the holographic description, let me just say a few words. And so those solutions are well known, and it is also well known the map. There is an explicit one-to-one map between those kind of supergravity solution and state in the dual CFT at the symmetric orbifold points, where you have this picture where you, well, the general state is essentially constructed from having elementary strengths of winding K and some SU2 left, SU2 right spin, subject to the constraint that you have N1 and 5 copy of the T4. And so there is a very well known map between this spin state and the lengths of the strands that appear in the states, which are specified essentially once you know the profile function of these two charge geometries. Okay. So here everything is well understood, and but we will take the simplest of all possible two charge solution, which corresponds to the circular, to a profile which is just a circular profile. Okay. And the reason why we focus on that is that the worksheet dynamics on a Lunin-Matur geometry with a circular profile is exactly solvable, okay, in the 5-brane decoupling limit. Okay. So that would this solution will be our sort of classical island, our starting point that we'll use for exploring okay, the phase space around this solution. So this, so I think I'm actually okay. It is easy to understand how to construct these Lunin-Matur geometries with circular profile. You can go to the T-dual frame where you just have NS5 and momentum. Oops, sorry. Where you have NS5 momentum. And the way to construct this solution is to start with some NS5 branes symmetrically arranged on a circle in the transverse space, okay? They wrap the T4 and the SY, and then sort of join all the strands together along the Y phi torus, okay, in order to make a single NS5 strands. Since this phi circle is contractible in the transverse space, in order to prevent this system from collapsing, one can stabilize them by spinning them up, giving angular momentum on the phi direction and giving some momentum along the SY circle. So this is a super tube configuration, okay? So once you know the solution corresponding to this solution, to this super tube, you can T-dualize along the Y circle, and you get the Lunin-Matur geometries with the circular profile in the NS5F1 frame. And the structure of this solution is that they are asymptotically flat. Then there is a 5-brane throat, and then there is a orbifold of ADS3 times S3, okay, in the Houppe region. in all the talk, we will work, as I said, in the limit where we decouple the flat space. So all our solution will be asymptotically linear dilaton, which is the solution that describes the fibrine throat and that interpolate between this UV region and the orbifold of the S3 times S3 in the IR. And so the dual state corresponds to just having n over k copies of strands of winding k. K is this orbifold parameter, which also control the angular momentum of the solution. So if you increase this parameter, you reduce the angular momentum, and you get closer and closer to the black hole phase along the line of two charge state. And what happens is that this supertube becomes more and more coiled as you increase this k parameter. So, sorry. So what I'm going to do now is to try to briefly review how we can get the worksheet description for this solution, and then we'll see how to use these techniques, the worksheet techniques, to explore the phase space around these two-charge fastball. So the key to get this worksheet description is to realize that this symmetrically arranged configuration of an S5 brane on a circle admit an exact description in worksheet theory in the near horizon limit, as this was known for quite some time, as an orbifold of the product of two cosets, SL2 over U1 and SU2 over U1. And that's a singular CFT, which is a sort of a capped version of the NS5, of the throat for a stack of NS5 branes. The cap is coming from this SL2 over U1 coset, which is a cigar. And when the branes comes together, the cigar becomes a long tube, which is the tube, in fact, dual to the little string theory that lives in the NS5 work volume, and you get this long tube. So there exists, in fact, an equivalent description of this CFT that involves a null gauging instead of an orbifold. Okay, and so you can actually describe the system by just well, at least the transverse space to the 5 branes by taking a product of SL2 times SU2 group manifold and gauge two independent U1 left and U1 right symmetries that are generated by the Cartan subgroups. And we can so understand, to make contact with the geometry and the metric and the B field sourced by this solution, we can analyze this coset by using a gauge Vesumino-Witten model. So where we start with the usual, where we start with the usual Vesumino-Witten model on the upstate group SL2 times SU2, and then there is a gauge part where there is a gauge fields coupled to the currents that are being gauged. The gauge fields enter quadratically in the piece, so you can integrate them out classically and get a sigma model from which you read the metric and the B field. And the metric that you get, okay, in some coordinate which are adapted to the SL2 and the SU2 group manifolds, looks like this. And you can convince yourself that, in fact, this metric is exactly the metric corresponding to having a bunch of 5 branes sitting at symmetric point on a circle, okay, with just sum over the harmonic function, in a limit where you have smeared the branes along this circle, essentially. Okay. So that's reproduced the geometry of this configuration. Sigma is the harmonic function. So this is 1 over the harmonic function in the decoupling limit. So we drop the 1 is 1 over sigma, okay, which appears as a quadratic, as a coefficient of the quadratic piece in the gauge fields. Yeah. So in fact, the information of where the 5 branes are, okay, is not lost. Okay, it's just not evident in the geometry. Okay. And it, in fact, can be reconstructed by non-perturbative effects in alpha prime, okay, which in this case are under control by using the so-called FZZ duality, which sort of relate the CGAR CFT with a theory on a tube with a Liouville superpotential that knows about the breaking of the U1 down to a Z5. So if there is time, I will come back to this, but for now, let's leave it there. Oh, sorry. What is it? Okay. And now it is straightforward to generalize this construction to describe the supertube, okay, that I was showing before. What we have to do is to tilt these NS5 branes along this Y-phi torus and make them rotating, okay? And it turns out, and the amount that we tilt this NS5 brane is specified by this parameter K. And this is in fact implemented, this tilting is implemented by a tilting of these currents that we gauge in the SL2 times SU2 group along a direction which is outside the SL2 times SU2. Okay, it's we need the gauge currents to points to have a piece in SL2 times SU2 and a piece in some external abelian direction, RT times SY. Okay, and with a constant of proportionality that is precisely this parameter K. So you can repeat the step and get the sigma model geometry that describe this solution. You get something like this. As you see that in addition to the metric of the NS5 ring that we had before, we added angular momentum and momentum along Y. Okay, and this is precisely the decoupling limit, the 5-brane decoupling limit of the NS5P supertube solution that was worked out by Samir Alunin. Okay, so again, this is a smeared version where we have smeared these NS5 branes along this Y-phi torus. Okay. So now we can do a T-duality along the SY circle. That's straightforward on the worksheet. It's essentially just a sign flip. And so exactly the same kind of model describe the NS5 F1 solution. Okay. And so we get this essentially worksheet description of the solution, which has this structure. We have the asymptotically linear dilator region that descend to a orbifold of ADS3 times S3 in the cap. Okay. Okay, so now that we have these nice tools, what we can do? Well, we go back to the good old days when string theory was a theory of strings, and and so we can do a lot of fun stuff. So, well, the first things that that we want to do is to analyze the spectrum of excitation around this solution. Okay. In particular, we want to construct the BPS spectrum. Okay, so we want to construct the vertex operators that describe the string state. Okay, that preserve some amounts of supersymmetries. And why? Well, for a number of reasons, but for the purpose of this talk, well, so we want to, as I said, so we sit at this particular point in the phase space of the microstate phase space, and we want to explore solution around it. So what we want to do is to construct the vertex operator that describes string excitation. If you think of exponentiating the vertex operator into the action, that will produce what? A perturbation of the metric and the B-field, okay, as dictated by the vertex operator that you construct. And so this will permit to explore, okay, solution around that particular circular supertube. So how do we do this? Well, we use the standard techniques, okay, which were well laid down for us by Emil in the glorious day of the worksheet. So we construct the Bersti charge, and we demand that the vertex operator lives in the Bersti homology So the structure of the BRST charge is exactly as in flat space. It's just now we are on a core space, and there's a well-defined procedure to construct the stress energy tensor and so on from the Pesumino-Witten model. In addition to this, we have some piece which is proportional to the gauge current and to its super partner, okay? And this piece with the gauging ghost, which are there because, well, this worksheet description, so we have this coset. The group upstairs had a bit too many dimensions. We were in actually 12 dimensions, 10,2. And we need to project down to the critical dimension. So we need something that tells us that the dynamics is actually the dynamics in the critical dimension. So okay, we have the BST charge, and then we construct the vertex operator. How do we construct the vertex operator? Well, as in flat space, okay, we use center of mass wave function, and then we decorate that with polarization. And so for the RT and the SY direction, this is just like you're used to in string theory in flat space. For the SU2 and the SL2 part, okay, the center of mass wave function carries some appropriate quantum numbers as dictated by a representation theory of the groups. For SU2, there is the spin J and the J3 quantum numbers, which is standard. And the representation theory for SL2 is a bit more involved because it's a non-compact group. You can work this out, and we will focus in this talk on a particular class of representation, which is the so-called principal discrete series representation, okay, where there is a specific relation between the spin and the M quantum number. And those, the state in this representation are the one that describe string states sort of bound to the cap of these geometries. So, yeah. We will have a 1D number, yes, on the SY circle, yes. Oh, sorry. Oh, well, I can repeat the question. The question was if there was a 1D number. I will come to that in a moment. Now, if we have these vertex operators, what do we do? So we need to ask that they are in the Beresty homology. These impose some constraints. One of such constraints is the usual Virasoro constraints that, for instance, here I'm showing this for NS state within supergravity, okay? And so this is a constraint that links together the SL2, SU2 spins, the energy, and the Y momentum. And then there are some constraints, which are linear constraints among the quantum numbers, which comes from the from this gauge current piece in the BST charge. Okay, and they comes with this parameter L1, L2, L3, L4, and so on, which specify the direction in which this U1 left and U1 right current is embedded in the upstairs group. For the circular profile, okay, this current points in a particular direction, and so this coefficient have a specific values that I showed before. We will come back later to a more general choice of these parameters. Okay, for now we just fix the parameters that correspond to the NS5F1 supertube. Okay, so this is the we have the vector operator, we have the constraints on the quantum numbers, and what we want to do is to construct the BPS vertex operators. So we need to construct the spacetime supercharge and determine the vertex operators that preserve a given amount of supersymmetry. So I'm not I spare you all the details. Okay, just try to from now on trying to just give the general picture. Okay, and the result is that okay. So let's first focus on 1/2 BPS vertex operator. So from vertex operators that preserve the same amount of supersymmetry as the two charge solutions. Okay. those vertex operators are constructed by using the center of mass wave function and then adding some polarization, like in flat space, where you have a graviton vertex, which is del x del bar x times e to the I k x. Here there is some constraint imposed by the supersymmetry, okay, and you have to select some spin J representation on the tensor product representation of the polarization and the center of mass wave function SL2. And the main point is that the states are highest wave states, so the M quantum numbers for SL2 and SU2 is equal to J, to the spin. The momentum along the Y circle is set to 0, okay, which is good because we don't want to add a third charge. Okay, we are just within the class of two-charge solution, but we allow to have a non-trivial winding on the. Yeah, there is a question.
Don't you want y tilde of z minus y tilde left of z minus y tilde right of z bar in the...
What is y tilde?
I mean, the winding vertex operator has a structure of y tilde left of z minus y tilde right of z bar.
Yeah, there's a py left and py right, which are y plus minus ny, y wyr plus or minus ny over r, right?
Okay.
That's so with the quantum number subject to the constraints that I just showed before. So now, what happens if you, in fact, exponentiate this vertex operator into the action? So this will produce, as in flat space, a perturbation of the metric and the B fields, okay, that perturbs your solution. Okay, we are sitting at the circular LM geometries. Those vertex operators preserve the same supersymmetries as the general two-charge solutions, okay? So what this perturbation do is to essentially perturb the solution that we are describing in this ensemble, in this set of just two-charge solutions. So it permits to explore, okay, the set of more general unimmature geometries in essentially perturbing around the circular supertube. So this vertex operator mediates transition to a more general, okay, unimmature solution. This you can actually you can convince yourself about this by matching the quantum numbers and so on. But that's what essentially those vertex operators do for you. So, of course, for now, we didn't learn too much. We knew everything about the two-charge set of solutions. So, okay, what we can do more? What we can do more is to look at vertex operator that preserve less supersymmetries. Okay, so we allow to break some of the supersymmetry, and what we do, we take here I'm just showing, for instance, the left moving sector. Okay. There would be an analogous right moving sector. What we can do is to keep the right moving sector as before, but we allow to break supersymmetry on the left moving part. Okay. And now the structure of the vertex operator change, and on the SY we don't have winding, but we do have momentum. Okay, which is good because we are indeed adding a third charge, the momentum charge. And then the SL2 and SU2 part are allowed to, not to be highest weight. So there are some parameters and an M which tells how much you depart from the state being a highest weight. I'm being a bit schematic, but that's the idea. Okay. Yeah. Yeah.
The helical geometry. The helical geometry of the 5 branes you have drawn in the left picture, that is already carrying NS5 charge and momentum charge because of the rotation, right?
Yeah, that's correct. Yeah.
So when you say you don't want to add the third charge, momentum is still included in the charge. Third
We are
charge would be the
not
winding.
adding. Sorry. No, we don't add momentum charge. We are, well, it depends. If you are in the NS5 F1 frame, you don't add momentum. Or if you are in the NS5P,
Right.
you don't add F1.
Yeah, I was just trying to see which one you are in. So right now, your background already has NS5 and P?
Oh, sorry. Yeah. So, well, yeah, you're right. Sorry. What I'm saying here is in the NS5 F1 frame, and I draw the NS5P picture. Just,
Okay, you change the picture.
Yeah,
okay. Yeah.
In the NS5 F1 frame, the information about where the fibranes is carried, where the fibranes are, is carried by the expectation values of winding operators in that duality frame. So it's not something that's geometrical or seen by supergravity. Right. So the advantage of the NS5P frame is that there's some very geometrical profile of where the fibrane is in its transverse space that's carried by ordinary, momentum carrying vertex operators. So in the NS5 F1 frame, that information about what the fibranes are doing is carried by the condensate of windings that fibranes are carrying. So it's not sort of intuitive and geometrical because it's some kind of properties of the winding condensate of the F1s. And so there's sort of two different things that are being described here. One was the half BPS deformations, where you're deforming the winding condensate to a more general winding condensate, which changes the background supertube. And now what Stefano is describing is if I stay with the same round supertube, there are also the deformations which add the third charge, and those are vertex operators that carry momentum in the F1 background.
Yeah, thanks. Yeah, that's indeed why we always like to draw things in an S5P frames. And yeah, I mean, yeah, I'll try most time to avoid getting to a bit more of the details on where the fibranes are, but thanks. Okay, so now, okay, we have those kind of vertex operator here. I'm just showing the one, for instance, with the polarization SL2, but you can, well, one can be systematic and write down all the possible vertex operators with polarization also in SU2 and in the T4 and so on. And there, also the Ramon-Ramon vertex operators, okay. So the question is what happens, okay, those vertex operator will mediate transition to an Houppe state, which is a three-charge state. So we start exploring this set of three-charge solution. Those are supergravity states, so the string oscillators are not excited. So this will just be a three-charge microstate solution. So what kind of solution do we get? Well, so the way to find out is actually to convince ourselves that there is a sort of a nice relation between the structure on the worksheet and the structure in the dual CFT. And one can sort of guess by matching quantum numbers that this dual CFT state that this vertex operator is mediating transition to is of this form, okay? And if you were paying attention to Anthony talks before, well, this is a very well-known state for a lot of people in the audience. It is a state which describes this superstrata excitation on top of this circular supertube. And in fact, the dual supergravity solution, the full solution dual to those states have been constructed, okay? And again, apologize for not putting, well, there's too many names to put reference to. So it's well known that it has been constructed, okay? And so the exponentiating this vertex operator into the action just leads to this kind of solution, which are known as superstrata. Then one can be more systematic and analyze, again, all the Ramon-Ramon sector and all possible polarization. And we realize that, well, we make transitions to a sort of a bunch of superstrata solution that people have been constructed during the, well, last couple of years, actually. including supercharged superstrata and 6T vector mode. And I think, in fact, I realized I never understood how to pronounce your name, sorry. Nates, okay, thanks. My apologies. Nates will actually talk about this, I think, and it will really show how to construct the full nonlinear solution corresponding to some of these, to the transition implemented by some of these vertex operators that we have. So I'll not, give all the details, but the points that I want to make is that, the advantage of using this worksheet technique is that we can be systematic, okay? So we can classify all possible vertex operators, so we can see we can chart the full space of solution we can get perturbing around this supertube. And we found that there is indeed a one-to-one map between this superstrato excitation and supergravity BPS vertex operators in our worksheet theory. Okay, so this exhausts the list of microstate geometries that we can get at least around perturbing around our circular supertube. Those, as I was saying before, those superstrata are known to give a subleading contribution to the entropy, so they are not enough solution to reproduce the entropy. And that's, somehow not so surprising, as in fact, string excitation seems to be missing the fractionation that one expects for the mode, at least in the cartoon valid at some point in the modular space that carry the black hole entropy. So so I'm a bit late, so let me just leave this comment there. Okay, so what we can do next? So that was the story, okay, for supergravity perturbation around the circular two-charge solution. So what we can do is to, change our starting point, if you want to. Just find another classical island, okay, and trying to perturb around this other point, okay. So we need some other solution that is amenable to a worksheet description. In fact, there exists a class of three-charge solution that are also under control in worksheet theory. And this class of solution arise from the so-called spectral flow operation from the two-charge circular supertube that I described before. So the spectral flow operation is a sort of a map that maps this solution, the two charge state to some three-charge state along this sort of parabola that describe the black hole phase, and it adds left and right angular momentum and generate a momentum charge. So it adds a third charge. And the worksheet description of those kind of spectrally flowed supertube, it's pretty much the same as the one that I described for the circular supertube. What one needs to do is to just consider the more general currents, okay, pointing in more general direction in the upstairs SL2 times SU2 times RT times SY group. So in general, we have, a bunch of coefficients that describe where these currents are pointing, okay? There's a constraint that those currents need to be null, okay? Because we want to do an independent left and right gauging. This leaves a lot of possibilities. And so the punchline is that if we keep the right U1 as before, and we only change the left current being gauged, we get a solution which preserves supersymmetry and have been constructed by Giusto, Lunin, Matur, Saxena, and David over some years. Okay, so these are very well-known solutions, and they also have a known description in dual state where you have equivalent SU2 excitation on top of the supertube ground state. If you actually change also the right moving U1, you get solutions which break supersymmetry, okay, and that have interesting properties. In particular, they have an ergoregion, so there is an interesting gravitational dynamics. And this is and the solution were actually constructed by known as GMART solution. They were constructed in 2005. Okay. So this is the decoupling limit. So we are always working the 5-brane decoupling limit. The solution have left-right angular momentum. They break supersymmetry. And this is, in fact, the most general solution that you can get, okay, with this kind of null gauging models, as David and collaborators showed a couple of years ago. So that's the most we can get, okay. What's J3?
Just to clarify your last statement, that this is the most general solution that you can obtain from this particular family of null gauging models.
Yeah, sorry, yeah, that's
the
not
J3,
well said, yeah.
Choice of J3 currents in particular.
Thanks, yes, yeah. Hopefully we can get more, but yeah, so what I meant is from this kind of, I mean, by using this kind of gauge current. Okay,
yeah.
Thanks.
GMART, there is also a family of black hole solution.
Yeah.
Are there included in this?
Good. So they are not in these kind of models. We believe they are there and we can get them, but well, you need to change. You need
in
to
the
change
GMART
the
solution.
current
There are black
gauge.
holes. Repeat the question.
See, yeah.
No. You go ahead.
No, the question was whether so in the GMART there is also a GMART family of solution which have horizons. Okay. Can we get those in the worksheet? I believe so, but we are working on this, in fact. But it's not inside this particular class of models. One needs to change the current spin gauge. Okay. Then one has to see whether the model is consistent or not. So there's some work to do. But that's an interesting thing to check. Thanks. Yeah. Sorry. Yeah, I'm actually much slower than expected. But so okay. So when well, we can start from this 3-charge solution. Let's say the supersymmetric one. Okay. And repeat the same thing that we did before. Okay. So we can look at the spectrum. Okay, and see what this leads to. So the structure of the vertex operator is exactly the same. So the 1,4-BPS vertex operator is exactly as I shown before. What is changed is the relation among the quantum numbers, because now these constraints change. They are sensitive to these parameters that define the currents. Okay, and these parameters are proportional to this amount of spectral flow that you do. So also to the angular momentum. So, oops. And so one can convince, it's easy to, it's easy. One can work out what's the relation between this kind of vertex operator and the dual CFT state that this vertex operator transition to. And, well, it has essentially the same structure as for the superstrata. So what you are doing is essentially adding superstrata excitation on top of this 3-charge spectrally flowed supertube. Okay. So in this case, okay, the geometries that arise by exponentiating this vertex operator, so that are dual to this state here, as far as I know, they've not been worked out. Okay, this will be just a spectrally flowed version of non-superstrata. Okay. So of course, this is just one case. You can repeat the analysis with, well, being systematic with polarization in SU2 and T4 and so on, and the Ramon-Ramon vertex operator. You get all these states, which are just literally spectrally flowed version of the states that are shown before. So you can easily construct this solution in the DS3 limit, but then coupling to flat space, it's hard, and well, it's an exercise that would be interesting to do. Those were actually described by Massai last year in a paper, so he was considering this kind of state. Then we can do the same thing for the non-supersymmetric solution, so perturbation around GMART. Now we allow to break supersymmetry both on left and on the right. So we have the same structure as before, but both on the left and both on the right. And the things works exactly as before. We just have a copy of this structure in the left sector and the same thing in the right sector. And again, the perturbation mediated by this vertex operator is not known, and they should lead to new microstrata solution, which are spectrally flowed version of the known superstrata, whereas spectral flow breaks now all the supersymmetries. Okay, so well, let me stop here for this part. I wanted to say a few words about this, but let's forget. Well, and then, okay, this exhausts all possible perturbation we can get in the supergravity limit. Okay. And now, since we have the full worksheet theory, okay, what we can do is to consider a vertex operator that describes string state where the constraints that I showed before are satisfied by turning on some string oscillators. Okay. And again, we can classify those vertex operators, and we can ask what happens when you exponentiate them into the action where they lead to. Okay, and here it's clear that since those are not supergravity state, we are start to explore this bigger region of the phase space, where the solution not just fully described within supergravity. So what should happen is that the solution corresponding to this kind of perturbation should be a geometry with an explicit perturbative string source. Okay. And it would be interesting to see if there is a generalization of the superstratas construction that allows a particular string source that will correspond to well, a solution as dictated by this vertex operator. Also, the holographic map for those state is not understood. Okay. So there are much more well, string state than supergravity state. We have a sort of control over them, but well, one can see that essentially, well, there's not much hope that this will help too much in reproducing the black hole entropy. In fact, those string excitations still lack the fractionation that you expect from the typical sector. And so it seems that, well, it's hard to get something with the right properties to be typical entropy carrying state around, by perturbing just around this super tube. So since I'm late, I don't have time to actually go through this, so I will just sketch what I wanted to say, and then I'll conclude. So, well, what we can do is to try to explore a more general region of the phase space. Okay, in fact, we can try to reach some singular limit in the phase space, where we might hope to find more degrees of freedom showing up and a larger phase space opening up with respect to this, well, perturbative string solution. And in fact, the idea is the following. So all these, well, microstate configuration are essentially coming from supertube configuration that arise in the Coulomb branch of NS5 branes, where the NS5 branes are separated and the brane that stretch between them are massive. One can try to move in the phase space to a point where all these branes coincide, and there is a transition from the Coulomb branch to a Higgs branch. Okay. And this happens when the D branes that stretch between the NS5 becomes light. When they become as lighter as the fundamental strings, well, string perturbation breaks down and the dynamics passes onto the Higgs branch. And for instance, this nice cigar for the NS5 configuration just becomes this long tube, which is dual to the little string theory that lives in the NS5 branes. And the little string are actually, well, the fractionated degrees of freedom that sort of seems to be responsible from the black hole entropy. And something similar can happen for the supertube. So if you increase this K orbifold order, what happens is that this supertube becomes more coiled and uncoiled, and these brains become closer together. So we have a similar sort of a similar picture. Okay. And in fact, so Emil had this nice discussion a few years ago, where the idea was that, well, for instance, here you increase K and you get closer and closer to the black hole phase. And one might think that the threshold of black hole formation is associated to a Coulomb-Higgs transition, where this, the dynamics is essentially dominated by this light brain. Okay, and one might hope that this sort of light brain have the sort of fractionation that that you expect from the typical sector of the phase space, of the typical sector of the microstate. And because of their very low tension, they might be able to live inside the black hole interior and do not feel the causal structure of the black hole. And that's what Emil was saying also this morning. So how we can get concrete result about this sort of brains? Well, we can study the brains in the Vesumino-Witten model. So in our worksheet setup, we can hope to describe the brains too, as we describe perturbative string state. We can also describe the brains. So I'll skip this because it's a bit technical. There's a very known way of construct, let me just say, of understanding the brains in Vesumino-Witten model. They wrap conjugacy class in your group. Here we have this gauged model, and so what we have to do is to start from some conjugacy class that describe your favorite brains and then smear them along the gauge orbit so that you can sort of get a state that can be projected out in the coset. And for instance, for the case of NS5 brains, there are the brains that stretch between the two NS5 that lead to S2 brains inside the SU2 group. And those brains have Ward volume flux. And from the quantization of the Ward volume flux, you can actually see that it's another probe of the structure of the, this quantization tells you that this DD brain should stretch only a special point where the NS5 brain sits. So it's another probe of the finer structure that is not visible in supergravity. And so then one can try to look for more general points in the modular space where some of the brains intersect and some of these D brains become light. For this one, we'll need some generalization of the gauged model, which exists. Okay, it's not an exact, explicit coset CFT, but we can have a 12-dimensional description of a more general unimaterial geometry, and we can look at points in the modular space where some of the strands collide, and those are the points where those some D brains is becoming light. So one example is, for example, to have a deformation of the supertube, circular supertube into an ellipse, okay, and then you consider a limit where the ellipse degenerate and the strands collide. And so that might be a way of probing more singular limits in the phase space, and we can hope that a larger phase space opens up where we might find the typical microstate. So let me conclude. So worksheet models are useful to explore the microstate phase space. The coherent state of all possible supergravity excitation are superstrata, microstrata solution. There should be a generalization of superstrata in which one allows some singularities which are resolved in the full string theory. Okay, and then one should probably look to some singular limit in the phase space where the dynamics is dominated by this light D brain state. Okay. Thanks.
Maybe time for one very quick pressing question in view of
So mine was saying 1 hour.
I thought that you wanted to avoid Raman fields because it's hard to describe them using worldsheet methods. So how do you describe d-branes in supertubes using worldsheets?
Well, I mean, we don't describe the backreaction of the brains. So if they would backreact, we don't know how to, right? But you can just, yeah.
Do you expect to be able to do some kind of superstratum construction on something like JMART?
Right.
Yeah, okay.
So, sorry, what
on JMART, superstratum construction on JMART?
Yeah, I think so. So, I mean, well, what that will be, Microstate. Well, I mean,
okay, yes, almost BPS, because it sort of smells like almost BPS construction.
Yeah, I think those solutions, I mean, in the ADS3 decoupling limit, the solution will be, you take the superstrata and you do the spectral flow. That will be the ADS3 decoupling limit of those solutions, I guess. Then the problem is how to recouple flat space. So that's, but I think it's just spectral flow. I don't know if Emil and David has more insight, but it's.
On the worldsheet, we would only see the linearized version of that. But as a supergravity problem, it's exactly as Stefano was saying. In ADS, it's a triviality just to perform the large coordinate transformation, but the challenge will be to add back the ones.
I think it's adding back the one that's the hard thing, because if you just do a spectral flow on asymptotically ADS, all you've done is a coordinate transformation, so it's still supersymmetric.
Sure.
So the supersymmetry breaking has to come from the gluing of the ones back into the thing.
Yeah, absolutely.
That's why I think it's kind of like almost BPS, because almost BPS is like you've got the supersymmetric object over here, and the supersymmetry breaking is done very far away.
Yeah.
You do a spectral flow, but then you change the identification. It's just a coordinate. It's not just a coordinate transformation, right? Because you change the topology of the identifications. So the supersymmetry is broken by boundary conditions. Yeah.
I mean, a cleaner way to say it is you get orbifold singularities deep in the core induced by this, in general, induced by this coordinate transformation, which in general breaks supersymmetry locally in the, like a Herzberg-Young singularity.
Like in JMART.
Yeah.
So that's